So hello everyone, this is lecture 15 for the quantum mechanics. In the last lecture we have seen that why we need Schrodinger wave equation. Okay, so we need it because we need to find a wave function for different kind of potentials and different kind of matter waves. So we need a general equation like we have for these real waves, this kind of. So we need some equation which can give us different wave function for different kind of potential, and we can define our matter waves. Okay, so we already see the why we need it. Now see what are the conditions or the plausible arguments which we need to get the means Schrodinger wave equation. Means what conditions should be satisfied. So plausible arguments leading to the Schrodinger wave equation. It must be consistent with the de Broglie and Einstein postulates. So whatever equation you will get, that must be consistent with this lambda and energy E. Okay, means this quantum energy h nu and this lambda de Broglie wavelength, lambda equal to h upon p. So that equation must satisfy these both equations. It must be consistent with the equation. This means it must be consistent with the conservative forces. The total energy is nothing but equal to kinetic energy plus potential energy, p square by 2m plus v. And it must be linear in wave function. Means whatever wave function you will get, that must be linear. Means if it is written in terms of phi1 and phi2, then it these c1, if this is equal to 0, then c1 and c2 must be equal to 0. Only then we can say that this is your linear equation. You know, when this is linear, these wave functions or whatever you will have here, they must be independent of each other and they should be orthogonal. Okay, means if you take the differentiation of this term, that must be equal to differentiation of this term and plus this differentiation of this term. So that's how we define something linear. So we already discussed in many lectures what is the linearity. Okay, so whatever wave function you will get, so that must be linear, and that's how your Schrodinger wave equation should be that way. So that wave function you are getting should be linear. Now see, Schrodinger never derived this equation. He just get this equation. But let's see how we can derive this equation. Okay, so we will see some way. Now see, we will derive a time dependent Schrodinger wave equation. So we will assume first any wave function. Okay, so for a free particle, this is not a wave function for free particle, but we are assuming this wave function. Okay, so because we need here just to find a differentiation, so that's why we can assume any function here. So we assume this as your wave function, psi equal to exponential I kx minus omega t. Now see, this psi xt equal to I px means we can write this in this form. How? Because here this k, we know how you can write the energy. You can energy in terms of h cut omega and momentum in terms of h cut k. So you can write these terms in this form, because h cut is nothing but h upon 2 pi, and 2 pi by t will give you h nu again. Here also h by 2 pi and 2 pi by lambda will give you what? H by lambda. So p by p equal to h by lambda. So you get these equations again. So this must satisfy this equation. So that's why we can write our equation in this form. So in place of k you can write p by h cut. In place of omega you can write e by h cut. So you will get this equation, px minus et divided by h cut. Okay, and free particle, for a free particle total energy is nothing but only kinetic energy. Potential energy is 0 for a free particle. So total energy E will be equal to p square by 2m. So remember these terms. Now we will find just the differentiation of these terms with respect to x and with respect to t. Then we find the equation for this. Okay, and then we generalize for that to find the Schrodinger wave equation. So let's see, first find the differentiation of psi with respect to x. So it will give you partial differentiation will give you exponential this, and this will give you iota k outside, and divided by, means if we are differentiating this equation, we turn this into this. Now differentiation of this will give you iep divided by h cut, and this term same. So differentiation with respect to x will give you this term. Now see, this is equal to again psi. So our del psi by del t is nothing but this is equal to this. Now you can find the second order derivative also from here. So that will be del square psi by del x will give you, means again this will be I p by h cut, then I square p square by h cut square. So it will be minus p square by h cut square and the psi x. So that will be your second order differentiation with respect to x. Okay, and from this equation, from this first equation, we can write p psi equal to h cut divided by I. So I multiply upside denominator and numerator. You will get here minus I h cut del psi by del t. So this will be your p psi equal to minus I h cut del psi by del t. And after finding the second order derivative, you will get this thing. So from here you can see that p square psi st equal to minus h cut square del square psi by del x square. So remember these two equations. This is first, this is second. Now let's find the differentiation with respect to time for this wave function. So it will give you exponential this and minus e by h cut minus I e by h cut. So del psi by del t will be minus I e by h cut del psi means psi xt again. And now from here you can see E psi equal to multiply I here and I here, so it will be I square will give you plus here and I, so it will be I h cut divided by means E psi will be I h cut del psi by del t. So you have this equation, this equation, this equation. Now see, this E is nothing but p square by 2m, so substitute here p square by 2m. So E psi will be equal to p square by 2m psi xt. Now this is again a equation. So see, this p square psi xt you can remove from here. So p square psi xt is nothing but minus h cut square del square psi by del x square. So in place of this, we will write this. This is again complete p square psi xt. So this is divided by 2m is equal to E psi xt, and E psi xt equal to I h cut del psi by del t. So it will be here. Now this is your differential equation for a free particle. Now here we have equation in terms of psi, so it can be anything. It doesn't need to be this wave function. This is equation valid, means he get this equation directly and we derive this equation from taking some any function. Okay, so whatever equation now you will get for the psi xt, that will be equation of a free particle. Okay, so this is the Schrodinger wave equation for a free particle, time dependent Schrodinger equation. Now let's see if particle is not free and this sum it is bound, means it has some potential, under some potential. So Schrodinger equation for bound particle means V is not equal to 0. Then energy will be equal to p square by 2m plus some potential energy depending on x. Now multiplying psi in the complete equation, E psi equal to p square by 2m psi xt and Vx psi xt. Now you know what is p square psi xt. From here you can substitute p square psi xt equal to minus h cut square del square psi by del x square. So this is equal to this plus Vx psi xt equal to E psi is equal to I h cut del psi by del t. So this. Now see, this is very well known around the world. This is time dependent Schrodinger wave equation. Time dependent Schrodinger equation for the bound particle. Now you can substitute potential here if you know the potential, and you can solve this equation to find the psi xt, and that represent the your wave function. Okay, for that wave, for that matter wave. Okay, so that's how you can find your wave function. Okay, from using this Schrodinger wave equation. So this was the way to derive, means this is not the original way, so you can check another ways also, but Schrodinger came to this equation directly. Okay, so he wrote this equation and we can use this equation to solve for psi xt. So let's see some more thing what we can do with this equation. When we solve the time dependent Schrodinger wave equation, it will give us the wave function of the particle as a function of time. That is how a wave function psi xt evolve with time. Means after solving this, we'll get some psi xt, and that psi xt depending on time. So we can see that how wave is changing with time. So we can just take this information out from this wave function, that how our wave changing with time. So it is called the evolution of with time. So that's how we can take this information also. And what information we can also take. So if we know psi xt of a particle at any time t, the different type of information of the particle can be extracted from the wave function. So what different kind of information will be? That is linear momentum, position, kinetic energy, total energy, angular momentum of the particle for which you have this wave. So you can find all these terms just using this wave function. How? I will tell you that we will have some operators, then that operator when operate on this wave function will give you the values of these things. Okay, so we will study about these operators in some coming lectures. So first let's see what we can do with this. So we can find these things. Now there is one more important thing here, that is preservation of normalization. Means what is the condition if we normalize a wave function, and if it is evolving with time, then what happens to this wave function. So that was a statement that it will remain same, it will remain normalized with time also, always. So Schrodinger equation has a remarkable property that it automatically preserves the normalization of the wave function. Means you don't need to normalize it again and again. At every step it will be normalized already. It means that if psi xt is normalized at t equal to 0, it will stay normalized for all future time. Okay, so this is a very remarkable property for this. Now see what is the meaning of this. Let's see some mathematical thing. What is the normalization? You know, normalization means this should be equal to 1, this probability should be equal to 1, particle should be somewhere. So this is your normalization, and if you take the differentiation of this should be came out to be 0. If your function is normalized, then this differentiation of this will be 0. So this condition should be satisfied. dy dt of psi xt equals dx should be equal to 0. If this condition is satisfied, then we will say that our function will remain normalized in every condition, because with time this is not changing, this will remain constant. So we need to prove this. So let's see the proof. So we need to find the dy dt of this. So we can write this thing, dy dt can come inside also, and if it came inside, then inside the integral, then this psi is the function of x and t, so this will convert into the partial differentiation. So it will be minus infinity del by del t psi xt square dx. So this can be written in this form. Definitely you can take the example like we have x here, this whole term equal to x, then integration will give you x square by 2, and differentiation again with respect to x will give you what, 2x divided, means you will get again x. Same here, if you have psi xt as x, so it will give you 1 here, and if integration will give you x here again. So this whole term will be equal to x, this will be equal to x, means you can take this form into this form. Okay, so now if this can be written in this form, we need to find this thing, del by del t of this psi square. Now how you can find this? See, this psi is a complex thing, okay, complex wave function, and you know from the complex numbers that a number which is complex, so it can be written a bar, a means a conjugate a is equal to mod a square. So remember this property there from there. So same you can apply here also. If you take the conjugate of psi, so psi star psi will give you mod psi square, just the simple property of complex numbers. So this can be written in this form. Now differentiation will give you use the product rule, psi star del psi by del t plus del psi star by del t psi. So this can be written in this form. So we need to find the value of this. So now we will use the Schrodinger wave equation that we derived. So this is your Schrodinger wave equation. Let's write it here. I h cut del psi by del t equal to this minus h cut squared by 2m del square psi by del x square plus v psi. Now see, this del psi by del t will be equal to I h cut will go this side, so it will be I h cut divided by 2m minus I by h cut v psi. This v is potential. Now this is equal to this, and we need to find this thing. So we need to find this psi star also. So what is the psi star will be? In place of I you will get minus, means this will be turn out to be minus. That's how you find the conjugate in complex number. So it will be plus I. Here also I, then here will be minus I. So this will be psi star and this will be psi. Now you can substitute these values here in place of this and in place of this. So you can find this value of this then again. Let's see after substituting. So this will be equal to psi star psi, means psi star del psi by del t, means this term, plus this term multiply psi. Now see, this is just multiply it inside. So this will be psi star I h cut by 2m and del square psi by del square minus I divided by h cut v psi star psi, and same for this, psi will came inside, so it will be psi star psi, and this with this it will be I by h cut v psi star psi. So this is equal to this will cancel out, plus minus, you will get only these two terms. Take this I h cut by 2m common, so from here it will remaining psi star del square psi by del square, and from here it will be minus del square psi star by del square psi. Now only these two terms are remaining. So to solve this, we can add and subtract these two terms, del psi star by del x, del psi by del x minus this. So these are same, so they will cancel out and you will get again the same thing. So you can write this thing in this way. Now why we written this thing? So we written this thing to get this form, means now del by del x, means this whole form can be written in this form. You can take this I h cut by 2m outside also, then you will see that del by del x of this term will give you this thing. How? First use the product rule, it will be del psi star by del x and del psi by del x, you will get this term, and then you will get psi star will as it is, then del square psi by del x square, so you will get this thing. Same for this term, you will get this and this term. So operating this on these terms, you will get this equation. So this complete equation can be written in this form. So only to get this form we did this thing. Okay, now how it is helpful to us to get this form? Now see here, to prove this, we have dx here. So if we get this psi x square del, means if we get this term in terms of dx, then we can solve this easily. How? Because here integration in terms of dx. So now if we are getting this value in terms of del by dlx, then you can integrate it with respect to x easily. So that's why we are using this. means we convert this form in terms of del by del x. Now see, this we find it, this is equal to this. Now we need to find this thing. So substitute in place of this, we'll substitute this thing. We find it here. So it will be del by del x I h cut by 2m and complete and dx. Now see, this is the form of like df by dx multiply dx and integration. So what you will get? You will get df and integration. So it will be f again. So whatever you are here, you are differentiating them and then integrating again. So you will get the same function. So this complete will be equal to this thing, and the limits will be put minus infinity to infinity. Now see, you remember that this psi wave function at infinity tends to 0. So this wave function must be 0 at infinity, minus infinity or plus infinity. So when you put the limits, this came out to be 0. Okay, because this should be, wave function should be 0 at infinity. So this will be equal to 0, and that's how we prove this, that this thing will equal to constant, and this is your normalized condition. And that's proof that evolution of the wave function, the normalized wave function will remain normalized always. Okay, so that's how we prove this. So this is a very important result, you must remember this. Let's see one more last thing for today, that is expectation value. So when we discuss uncertainty, we discuss that how we can write our average or expectation value in terms of probability. So if you want to find the average of t, then it is nothing but t and probability of t. So it will be summation for different values. And if it is you want to find the average of t square, it will be just t square here and probability again. So that's how we define there. Now see, if we need to find the expectation value of x, so it will be x and probability x. So what is probability x here in the quantum mechanics? We define probability as this psi xt square and dx. We defined this probability in this form. So this was for the discrete data. For continuous data you have integration, because for all data you must be adding all these values. So it will be integration. So x psi xt square dx. So this will be your complete expectation value. Now see, this can also be written in this form. Expectation value will be equal to psi star x operator psi dx. So how can we write this form into this form? So we'll study about this, that what is this operators and things, because this is position operator. So we'll see about them. But here you need to remember that you can this can be written in this form, and we will see the proof that how we can write this into this. So let's see the proof. So first we need to find that how this changes with time, means how this expectation value changes with time. So d average divided by dt is nothing but first write the value of this average will be this, and divided by dt. So it will be d del psi square by del t. Now we already find it this thing. Just now we find it this thing as equal to this in terms of del x. We already find it this. So we can substitute here this thing and dx. So this is again the same thing. Now see, you need to integrate this. So what you will do here, you will use the integration by parts. So you will take this as first function, this is complete as your second function. So this will be, means now this is in this form. You take the constants out, these, and this is x del by del x. Now you will use the integration by parts. So take this as your first function, this is your second function. So first function as it is, the integration of second function will give you this function as it is again. So we already discussed how we get this, because it is del by del x and integration again. So you will get this as your integration. Now put the limits minus infinity to infinity, then minus differentiation of first function, that will be 1, integration of second function, this will give you this, and then again integration. So this is your integration by parts rule, you know this from the mathematics. Now I h cut by 2m, see this will be 0 again because limits are infinity and these functions are 0 at infinity. So this will be 0, only remaining thing is this. So minus integration psi star, we will separate these terms. So it will be psi star del psi by del x, minus plus del psi star by del x psi dx. Now see, we will apply the rule again, the integration by parts. So we will apply it only on this integral. So this will be our first function, this is our second function. So first function as it is, integration of this second function will give you psi star, limits minus infinity to infinity, minus differentiation of first function. So it will be del psi by del x, second function integration will give you phi star, the integration again. So this is equal to 0, same reason here as here, same reason here also, it will be 0. Now you have the same function here, so it will be minus 2. So 2 will cancel out, you will get minus I h cut by m, and this psi star del psi by del x dx. Now see, this will be equal to, means this is something like velocity. See, this is your average position vector. So not vector exactly, it is your expectation value of position. So this is something like velocity. You can see the dx by dt. Now if you multiply with mass here, so it will be something like momentum. So you can write m dx by dt equal to this thing, mass will multiply, so mass will cancel out here, I h cut by m, so m will cancel out. Now see this thing, this minus I h cut will be inside, so it will be psi star minus I h cut del by del x and this psi and dx. Now in the coming lectures you will see that this is nothing but momentum operator minus I h cut del by del x. So we can remove this term with p operator. So it can be written in this form. And now see, this is your, if this is your velocity and momentum, then this will be expectation value of momentum. So it can be written in this form. So this is the result for the momentum, means expectation of value of momentum can be written in this form, psi star momentum operator and psi dx. Now this result is applicable for every operator and for every case. So in general you can write for any a operator, you can find the expectation value of a equal to minus infinity psi star a operator psi dx. Okay, so for position also expectation value of position will be equal to same. In place of a operator you will get x operator psi dx. So you can apply this result anywhere for any operator. In the coming lecture or the next lecture we will see about the operators in detail. Then we will see about the tools of the quantum mechanics. So that will be a very heart of the quantum mechanics, we say about the tools. So that's it. Today we will stop here. Thank you everyone.